Martí, Rosselló. This morning, coming all the way from Taiwan. I hope the jet lag is all right.
All good. So thank you very much. I'm very happy to be here, really. And so I first wanted to say that I was thinking about talking about black hole matrix accounting, mock modularity, and how using modularity one can prove a conjecture for the sign of the index. But in the end, I decided to change topic, but I'd be very happy to discuss about it so at any point, any coffee break or lunch. But today I decided to talk about the giant Graviton expansion. Okay, can you see? Okay, so the title of the talk is the giant Graviton expansion in AdS5xS5. And this is based on work with Georgios Eleftheriou. And Samir Murthy. So we started thinking about this last year when I was in London. So I also want to say that there will be no explicit modularity or resurgence, but this topic actually has links to both. So I'll try to mention them when they appear. Okay, and I'm confident that there's more to come, but this is the beginning of the story, I would say, and that's also why I wanted to talk about it. Okay. So the context of the talk is just holography. As you can imagine by this AdS5xS5. But the idea today is that at finite n. Okay, that's the idea. And in particular, so we want to understand the finite n effects in the boundary and also in the bulk. And since G string goes like 1 over n, taking n to be finite means that you need to take into account non-perturbative contributions. So okay, so this is a hard question, and of course what we'll use is supersymmetry, and in particular we'll study supersymmetric indices. Okay, so one can think about this talk as so holography in this talk would be a Q series identity. Okay, so don't worry if you don't know where is the giant graviton or where the giant graviton expansion is. I'll try to explain all this. So first of all, why supersymmetric indices? So if you take supersymmetric quantum mechanics, you can define the Witten index as a trace over its Hilbert space, but with an insertion of -1 to the f, where f is the fermion number. Where these are the supercharges, which are square to the Hamiltonian. And these supercharges send bosons to fermions and fermions to bosons. And they don't change their energies. So this means that the excited states are paired by these supercharges, and they do not contribute to this index. Okay, so for super quantum mechanics, this is basically just the only states that contribute are the ones that are annihilated by these supercharges. So therefore, this is just the difference between bosonic energy zero states minus fermionic energy zero states. Okay, so this is just the difference between bosonic and fermionic ground states. And the interesting thing about this is that as you deform the theory preserving supersymmetry, this does not change. So this is invariant under changes of the coupling, which preserves supersymmetry. And you can define a similar index for superconformal field theories. So these will be, they are basically the same. But now you can have many more supercharges. Okay. So now instead of just ground states, you can be counting states which are annihilated by a fraction of the supercharges. Moreover, you can refine them with some by labeling them by the eigenvalue under some operator that commutes with these supercharges. Okay, so this is just a refinement of the Witten index for superconformal theories. And now again, you could say that maybe what we're counting, since there are so many cancellations, it's not very meaningful. But just so, let me just motivate why this is not true. So for the 1/16th BPS index in n equals 4 super Young Mills, okay, it was long suspected that that was the case, that there were too many cancellations and this index was not meaningful. But it turns out, so let me write this index as a Q series. Okay, the question is if these, the generacies counted by this index are capable of reproducing the black holes which preserve 1/16 of the supersymmetry in supergravity. And so the question was, is this number, when n goes like n square, this should capture the growth of the black hole entropy. And this was shown a couple of years ago to be true. Okay. So this means that even though there are so many cancellations, these supersymmetric indices, superconformal indices, still capture relevant physical quantities. Okay. So this is just to motivate why I'm looking at these objects. This one will not. This is independent of beta. Let's say yes, because it's easier. Yeah. So, okay, this could be, you put it on S3. So on, okay, so now the index of interest today will be the half BPS index, which is the simplest non-trivial index, I would say, because it counts states which are annihilated by half of the supercharges. Okay, in this case, it was only 1/16 of the supercharges. Now this is half of the supercharges, so they're really constrained. So since I can study this independently of the coupling, for n equals 4 super Young Mills with the gauge group UN on S3. This reduced to, so in the free limit, computing this index is reduced to combinatorics. Okay, this was maybe in 2018, I think, by Cabo Bizet and collaborators. So, and this is some old results. So, but just let me show you how these finite n corrections appear. So these half VPS states are, so I put the conformal field theory on S3, so now I have this state operator correspondence, so I can just count gauge invariant operators. And these half VPS states, depending on the half of the supercharges that you choose, are just created by the operator, which is, let me call it X, which is a complex scalar. Okay, but now I have to take gauge invariant operators. So what I can do is choose the trace basis. If I take the trace of X, it's gauge invariant. And then I want to label them by some R charge. Okay, so the half VPS states satisfy this, where this is the scaling dimension, and this is some R charge. And I want to compute this index. Okay. The half VPS case is a bit special in that you have to reduce your trace to the half VPS sector, so that's not very informative, but okay, it is how it is. And okay, if I want to count how many states I have for a given R charge, so this operator has R charge 1, okay? So I take traces. If I have 1 power, I have 1 operator, which is trace of X. For R charge 2, I can have 2 possibilities. I take trace of X square or trace of X square. For 3, I guess you see how it goes. There are 3 possibilities, and so on. Okay, so this is, so there will be charge 1, charge 2, charge 3, and so on. So this would be just counted by all the possible partitions of the R charge. But of course, at some point this stops because of the following. So since X is valued in this Lie algebra, well, that's this statement is independent of this. So X is an n times n matrix, and what happens is that the trace of X to the power n plus 1 is a function of the lower traces. Because X is n times n. And this is a consequence of the Cayley-Hamilton theorem. Okay, so these are the trace relations. And this means that this index here, let me call it I1/2 n, will be given by all the possible partitions for a given R charge, but with where the maximum size of the partition is n, okay, because at n plus 1, these are not independent. Okay, so therefore that means that this index has this very nice closed form, okay, where Qn is the Pochhammer symbol. Okay. All right, so everything that I've said now is well known and trivial and simple, let's say, but now let me say what we, so Now we have some quantity in the boundary, computed as in the free limit. And now I would like to know what to expect from this index. What do I expect to see it in the bulk? Okay, so take a general index. Okay, what our expectations are the following. When n is, so when the charge of the state is much smaller than the rank, so this is like taking n to infinity limit, this should just be the same, agree with the supergravity answer. Now when n is of the order n square, if there are black holes preserving the same number of supersymmetries, this should agree with the black hole degeneracy, so the degeneracy of black hole microstates. And when n is of the order n, this is the typical scale of a deep brain. Okay, so we should start to see some disagreement here. Yes? So typically one starts with n to be infinite and then one thing is lower, but here n could be 1. Here could be as small as you want. So for the thing here is that the half BPS limit is the half BPS case is very special, and the derivatives. So if you take the derivative of this operator, then it's not half BPS anymore in the free limit. So usually when right. On the other, what was the other question? Mm-hmm. Yeah. Yes, yes, they are annihilated by half of the supercharges. So here, this is an exact statement for any value of the coupling constant. But okay, we can discuss more later. So these are the expectations, okay, and these are borne out in the giant graviton expansion, which is the following statement: given a superconformal index, which has a holographic dual, you can always write it in the following form. Okay, here this parenthesis n doesn't mean derivative, it just means some n dependence. So the statement of the giant graviton expansion is that any index which has a holographic dual, should be it should be possible to write it in the following form, which is just you can factor out the n going to infinity limit, and then you will have an infinite sum labeled by m, where all these terms, so this is a Q series which starts at power at least mn. Okay, this is some general expectation. This has been proven for, so maybe let me say that this was first studied by Imamura and corroborators. Then Gayot only so Imamura studied this in the bulk. He showed that if you start computing contributions from D branes, you can start correcting the I infinity index. So somehow experimentally. Then Gayot only showed again experimentally in the bulk that you can always find this structure looking at your indices. And then Martí showed that if you have any, so from any matrix integral, a unitary matrix model, okay, you can always express it in this form, okay, just from using some math decompositions of these integrals. Okay, so in some cases it's very general, in some cases it's experimental. But for the index that I want to study today, so there is no conjecture, this is just a Q series identity. So for the half BPS index, let me write it here. This is true because this is an exercise that you can write it in the following form. Maybe let me erase this. Okay. So this is the giant Graviton expansion for the half BPS index. Okay. Right. That's what I'm. That's where it's coming. Okay. Now I explain why the name. Okay. Thank you. So okay, but before that, just let me make some comment. So indeed, let me see where I can write. Okay, first thing is, indeed, just from this form and from this conjecture form, we see that these corrections, this term, starts for the case m equals 1. So the index agrees with the n to infinity answer until the power hits capital N. Okay, and then it starts disagreeing. We see some grading. And we expect this to be coming from m number of branes. Okay. And finally, so this is one of the connections to resurgence. I'll write it here. Is the following another Q series identity? Is the following. If I write the Pohammer symbol of Q to the minus 1, and I expand it in Q, where I get is the following. Okay, so you could think of this index as being counting states with negative R charge now and expanding it in the other direction. Okay, so this, if I expand it in this region. Okay, so this that means that Imamura actually computed things in this way and then performed this analytic continuation and obtained this form. Okay, what we want to do today is to obtain this answer directly from the bulk without any kind of analytic continuation and see if there is some physics to it. So one thing is that in this one, here there are no black holes. There are no black holes which preserve half of the supersymmetries. Okay. In the 1/16 BBS case, things are complicated because, again, because of this, the giant Graviton expansion is not known in closed form. It uses this analytic continuation, and you need more fugacities, meaning that it depends on. So it's not so simple that you expand inside or outside the unit disk, but there are different regions of convergence. The of this, yes. Let me see, maybe here. I hope I remember it correctly. So I think that the matrix integral is the following. So this should be some integral over your gauge group of the plathistic exponential of the single particle index. So the single particle index for the half EPS index is just Q, because you have X, and that's the only thing you have. So this should be, if I remember correctly. So here there is some measure, and then you have to plathistic exponentiate. And now this had to do with the character of UN. And I think it was this one. I'm not 100% sure, but I think it took this form. Takes this form. So on what Samir showed is that from this integral representation, you can always get to this form. Okay, and I think, yeah. So for more general, if you take more general single particle indices, it doesn't matter how complicated you write it, it will always have this form. That was the point of Samir's paper. All right, so why giant Graviton expansion? Yeah, maybe should accelerate. Right, the name doesn't say much if you don't know what is a giant Graviton. So that's it. That's everything I want to say for the boundary. Now we go to the bulk, where the giant gravitons appear. So bulk. It's AdS5 times S5, and I have n units of flux here. Now we can have D3 branes in this. So this is type 2b string theory, meaning that I can have D3 branes in this background. And in particular, there's the following D3 brane embedding. Let me write the S5 metric explicitly. okay, where theta takes values between 0 and 2 pi and pi halves. Okay, and giant gravitons are some particular D3 brane configurations which are spherical inside the S5 and which preserve half of the supersymmetries. And moreover, they are rotating. So spherical branes would collapse, but by the rotation, they are somehow stabilized. And now the idea is to wrap a D3 brane wrapping this S3 sphere. Put a D3 brane here. So you should then compute the exaction. That's the dBi plus the Chern-Simons term due to this 4 form. So maybe that's the induced metric. That's the pullback of the 4 form on the wall volume of the brane. And the brilliant thing now is the following ansatz. So you take theta to be some constant, and you take this angle phi to depend on time. And you look for solutions to the equations of motion with these ansatz. Yeah, Dirac-Born-Infeld. Yeah, thank you. And all right, what this was first shown by McGreevy, Seskin, and Tumbas, that this was a solution to equations of motion. And actually, what they found is that this will be a solution to equations of motion if it has to move it has to rotate, this D3 brane has to rotate at constant speed around this circle. Okay, so maybe let me draw what they found. So these D3 branes, which are stable, this would be the angle phi, this would be theta. This is 0, and this is pi halves. These branes are rotating around phi. They are some S3. And when theta is 0, they collapse to a point. And when theta is pi halves, they are the maximum size, max. Okay, that's because, as you can see from the metric, the size of this D3 brane, so the radius of the D3 brane, is L sine of theta. Okay, and very importantly, they carry angular momentum. Okay, all these branes. So maybe let me write it here. They carry angular momentum due to this rotation, and it's given by this. And in particular, this has a very nice consequence, which is that the angular momentum that these branes carry is bounded by n. Okay, so that was the point of McGreevy and collaborators, is that so in n equals 4 super Young mills, you see these finite n effects through these trace relations. In AdS5 times S5, you see them through the maximum possible size that the brain can have. Okay, you have a brain inside S5, it cannot grow indefinitely. So the bigger it is, the more angular momentum it will have. But at some point, the size is bounded because it's inside S5. Okay, so right, and now why the name? So these are called giant gravitons. Maybe let me erase this. So that's one nice message from the early 2000s. And two more things about this is that if you think about the Hamiltonian taken from this Lagrangian, just as a function of theta. So given some angular momentum p phi less than n, okay, the Hamiltonian as a function of theta has this form. You can plot so it has two minima. This is the D3 brain, where the size will be given by this this theta 0. So this value here will be the theta 0. But there is another minimum, which would be the one representing just the graviton. So the graviton and the D3 brain are basically the same quantum state. They carry the same quantum numbers. There are two degenerate minima. So you identify them. And that's the point of these giant gravitons, that they just from the bound on their size, they're putting a bound on the angular momentum. Okay, so that's why they are called giant gravitons. And I should say that there's a nice follow-up paper called Suzy and Goliath, which is very appropriate for this city, which says that these D3 brain configurations, the first analysis was just looking at the bosonic, so the bosonic Lagrangian. They showed that these are half BPS. Okay, so they are really, they preserve half of the supersymmetries. So it depends. If you fix some angular momentum, then the theta 0 is the value that the Hamilton gives you. So exactly. So a graviton can have any angular momentum, but if you identify them as being linked to this giant graviton, then it has a bound. They are separate a priori, but then so a priori they have nothing to do with each other for a graviton, but for a giant graviton, you see that the angular momentum is bounded of the giant graviton by n. Yes. Yes. Exactly. Yeah. They are. So the terminal operators are actually dual, if I'm not wrong, to the maximal possible giant. The subdeterminant operators are dual to smaller giants. Yes. Yes. Exactly. The only. Okay, okay. So the maximal bound will appear shortly. It might be, yeah, it's possible, probably related to this. Exactly, and very good and very nice, very nice. And I think so. That's because the angular momentum now is stored in the gauge field. Everything is there. No rotation, but maximum angular momentum. Okay, so once you have these solutions, you can of course study the fluctuations around it. This is to motivate what will come. So they were studied again 25 years ago by Das, Matur, and Jebicki, I think, and they show that in this range, basically they are gapped. They are kind of like a harmonic oscillator. Okay, and now what happens is that when theta 0 becomes pi halves, so for the maximal case, this I think was overlooked. I'm not 100% sure, but we didn't find it anywhere. The moment you go to the maximal case, if you look at the Lagrangian coming from this action, it has the following form, maybe with some constants, but it will look like this. So there will be a small fluctuations in theta and phi. Okay. Now this might not be very informative. So let me. If you write it in different coordinates, which yeah okay. If you write it in different coordinates, then it becomes very transparent of what it is. So let me ignore this term, okay? So ignore. I change coordinates to Cartesian, and I get the following Lagrangian. Now let me write it with the proper constants. Okay, so this is the Lagrangian of a particle moving in 2 dimensions with a constant transverse magnetic field. Okay, this is the Landau problem. So it's just 2D plane with some magnetic field. And I didn't write, so this term that I ignored, it's a flux term, meaning that it's a, so by this I mean an infinitely thin solenoid through the origin. Okay, so it will be like a delta function term. Okay, you probably know this, but let me write it. If you write the Hamiltonian, so this is the Hamiltonian associated to this can have the following form. So has the following form. where here I perform canonical quantization and so on. So this is the 1D harmonic oscillator. And what this means that, so we have some energy levels labeled by n. This means that each energy level, so we start with 2D, now we have a 1D. Each energy level is infinitely degenerate, and these are called the Landau levels. Okay, and for n equals 0, so the lowest energy level, this is the lowest Landau level. Now, if you want to break the degeneracy, you can use some other operator using the symmetries of the problem. This Lagrangian has rotational symmetry. So with the angular momentum operator, I can label states at each energy level. Okay, probably you all know this, but so that means that I can label my states by 2 quantum numbers. And in the lowest Landau level, this angular momentum operator has the following spectrum, where L is some non-negative integer. Okay, so I have so the spectrum of small fluctuations around the maximal giant has infinitely many ground states, and I can label them just so. Okay. So with this, I wanted to motivate what we will do next. And before I forget, with the flux, so if I add the flux term, what will happen? The flux term doesn't change the Hamiltonian. It will just shift the eigenvalues of the angular momentum operator by, it's not clear how to see it right now, maybe because I didn't write the constants here, but the shift is by n units. Okay. All right, so this was a long introduction to giant gravitons, but I hope you didn't know too much about it, so that you learned something. And now what we wanted to do, so we want to do holography, right? I talked about how to understand these finite time corrections in the boundary. In the bulk, we saw that they appear through these giant gravitons. So now let's try to compute this index in the bulk. Let me erase maybe this one. Right, sorry, I forgot to say it. The dual to the R charge with that choice of R charge that I had somewhere is L.
Oh, sorry, yeah, that's the JZ component.
Exactly. Yeah, thank you. That's the R charge in n equals 4. That's how the dictionary. Very good. So now we had, yes? Exactly. So in the boundary, it was this trace over the half BPS sector. This was boundary. Now I want to compute it in the bulk. So I have to take some trace with a -1 to the of insertion over the half BPS subspace. So our proposal is that, so we know where are the half BPS, so where is the half BPS spectrum now in this pro-brain approximation. They are just given by these giant gravitons. Where you can have also no giant graviton. Then you have to iterate over this moduli space of giant gravitons. So in principle, so parameterized by this theta angle. And you can have arbitrarily many. And then I have to iterate with periodic boundary conditions due to this -1 to the f insertion. And now I weight the action, I take the supergravity plus brain action. And I insert this q to the r operator, which is just this associated to this angular momentum operator. Yes, because this is a path, so this should be a path integral in AdS5xS5 in string theory. This is not something that it is really well defined, but since we are only restricting ourselves to the half BPS sector, this is more under control because we know what are the possible contributions. And what we are assuming, so that's why I say proposal, because I'm assuming that there is no really back reaction. Okay, so maybe this is related to Masazumi's talk yesterday, which I don't assume that there can be any kind of back reaction. Yes, yes. Right. So yeah, this is kind of a hybrid thing because we are already taking into account brains. When they varieate, they produce these bubbling geometries, but we are not in that regime. So right. M here is how many giant gravitons you have, because you could have, so you could have one here, one here, one here, one here. They could be coincident. They could be anything, and you integrate over all of it. Right. So. And
at that point, in the case where you have black holes, do I need to add by hand the black hole part, or does it come out of some double scaling limit of the giant graviton? If I put n giant gravitons and n scales with n itself.
Very good, very good. So this is the, thank you. This is one of the whole points of the giant graviton expansion is that the whole index should come just from the brain contributions. So you don't need, so just counting states on brains will give you the black hole megastates. All right, so I'm sorry because I was a bit slow. Now our idea of how to treat this integral is the following. We study the supersymmetry on the brain. Okay, and on the half BPS sector, one can show that there is a set of supercharges that satisfy this. Okay, so which geometrically would be okay. And now our idea is to perform a localization. And so we have this complicated path integral, but we have supersymmetry, so maybe it can get localized to a subspace. So the idea of localization is you have some partition function as a path integral. So you deform it with some term. So this has to be supersymmetric, meaning that QS has to be 0, and this term has also to be supersymmetric. And so maybe in Euclidean, where things are somehow better defined, one can show that this actually does not depend on T. So yeah, sorry, I will not. So I can try to explain it better later. And therefore, you can take the T going to infinity limit. The answer should be the same. And this will localize to the fixed points of this. So I just have to look at the fixed points, so at the bosonic fixed points of this functional. And in our case, the fixed points are related to this. So this has to be 0. And it turns out that the fixed points satisfy that both this one and this one are 0. So the only giants which are rotating that satisfy this are the ones at the top. Okay. There are other ways to argue for this. So in Euclidean signature, actually only the maximal ones survive. But that's not what we did. And okay, so the fixed points will be these ones. And when you perform this T to infinity limit, so you localize your path integral to the fixed points, and it gets reduced to just the quadratic fluctuations around these fixed points. Okay, that's the whole point of localization. And now, what are the quadratic fluctuations of this action near the fixed points? So the supergravity fluctuations are just the so at the quadratic level they decouple. You will have the supergravity fluctuations and you have the brane fluctuations. So that means that this path integral will factorize. So you have to compute the determinant of these quadratic fluctuations. This will give you the supergravity index, which is just the I infinity index. So that's one of the main points. Why do you have this factorization? It's due to this localization. And then you have to compute the index on the brane. Okay, so maybe now there is no iteration over the moduli space because it's just at the maximal for the maximal giants. And now this should be the let me write it I m brane index. Okay, where this is maximal. And these are the quadratic fluctuations. So this in principle would be a path integral, but of course I can compute it in the Hamiltonian formalism, which is what I already did. So the quadratic fluctuations look like this. You have this Landau Lagrangian. You have to add the fermions, because I was just looking at the bosonic part. So if you add the fermions associated to these bosons, you will have a pair of fermions. Maybe let me write what you get. So maybe write it here. So for one giant, you will have this Lagrangian plus fermions. Okay. And now maybe just let me write the eigenvalues that you will have. So now you'll have 4 quantum numbers. on this. And the angular momentum operator has these eigenvalues. Now, importantly, we are computing an index, meaning that I'm labeling states with a -1 to the f. This -1 to the f, you can operator for this problem has this form. Okay, so again, you have infinitely many cancellations between up and down states. So when you go down, you can, let me see, right, and you take one more energy eigenvalue, it will cancel with the previous one. So the only states that survive are these ones. So yeah, sorry, I didn't mention that S take the values plus -1/2. Okay, these are the fermionic eigenvalues. All right, and so this means that now your angular momentum operator on the states that survive has this form. So this fermion just induced a shift by 1. And yes. Yes. But this, so that's true, but so H minus R is for the, let me think, this for the whole problem. Now this Hamiltonian is not the same as that one, this is just the quadratic fluctuations. Okay, and here I didn't include the flux term, so if I include it, it starts at, so plus n, so that means that for one giant, with this, this -1 to the f will give you a -1, so this would be this series expansion, which I can write just as okay. And if I compare it to the giant Graviton expansion that I erased, this will be the first term. Right, this would be the first term. And then when I put m giants, this will be the matrix version of this problem. It's not, it could be very complicated because you have now two matrices and only a UM gauge symmetry. So you have to diagonalize it, and in principle it's not possible. But the nice thing about the Landau problem is that the Hamiltonian gets reduced to just a one matrix problem, and then you can diagonalize it. Okay, and if you do so, you would get the full giant Graviton expansion, which is given by this. Okay.
So this is telling you that the minimal configuration of that is really a fermionic one. So that's what we mean by that.
So I think that what's happening is that one thing is the full Hamiltonian, which you have no control over it. And the other is once you perform localization, you have a different problem. You're studying the quadratic fluctuations, and the minimal one is fermionic. Right, right. Yes. No, yeah, I was very confused about it. Yes. So in the boundary, half VPS states are bosonic. That's it. But we are saying that, so in the bulk, we don't really know, but if it's true that they come from this localization procedure, that doesn't mean that the half VPS states are fermionic. It's just that the way to compute it, the way the bulk sees, the way the bulk localizes this path integral is through these fermionic contributions. So we are not saying that the bulk, the half VPS states are fermionic. We are saying that through the localization, it so the path integral gets localized to some auxiliary problem, and here you have fermions. That's our take. Right, sorry I didn't write it. So what we saw is that this Lagrangian with the fermions is Q exact. So you add it, and it looks like it's just the full Lagrangian that is Q exact. The fixed point is this one. Mhm. Mhm. This one? Right, right, right. Okay. Right, right. Very, very good. Yeah, maybe. Yeah, sorry, I didn't. The thing is, I erased the answer that I didn't want to erase. But okay. So it's what you have is the following. So the full answer. The full answer is this one. So what we showed is that that's the one giant problem. Two giants will be 2x2 matrices, 3x3 matrices. It's just the same Hamiltonian but matrix version. And now if you think about the n to infinity limit, so this starts at 0, which is, so this would be I infinity q times 1 and then minus this plus now let's see, it should be 3 1 minus q minus and so on. So that the n to infinity limit, since q, we are always taking this to be smaller than 1, it's just this. And then the corrections will come.
If I didn't know about the Django, we just read in theoretical integral, if I go to logic expansion, I will get some settle points, I will expand with settle points. Will I get it? A question more or less, this expansion has a question. Is block corresponding to settle points?
Okay, that's a nice question. I'm not. So the thing is, I know that from that matrix integral you can write it in this form, but I'm not sure that if you do this saddle point expansion you will get this factorization. I don't know what you would get. I don't know. So you have two maximal giants which are coincident. So you get you would write this Hamiltonian, not this one because that's just the spectrum. You take the Hamiltonian that you get and you yes, exactly. And then you have to diagonalize it, but the Landau problem somehow lets you do it. Right. Very good, very good. That's exactly what Gayotto only did. So Gayotto only, instead of looking at traces, they looked at determinants, and modification of these determinants showed that that was the reason for obtaining this form. Exactly. Very good. Right, so I forgot to say all this. One is that for the half VPS case, of course, this is the Q infinity Pohammer, which is the Kineta. So that's a simple way in which modularity is somehow here. And then when as you take n smaller, then you lose modularity. That's just one comment that I don't know if it's very deep. Now, the role that modularity plays here, for me, I don't know about the n infinity, why it has nicer modularity properties than finite n. But, okay, yeah, I don't know. But one thing I want to say is that for the 1/8 VPS case, that's the Schur index. And it's known that the Schur index can always be written as, for the n equals 4 Cipriani Mills, it has known expressions as in terms of quasi-modular forms. Okay, so this means that this giant Gaussian expansion, again, this will have some modular per factor, some this expansion, so some giant Gaussian expansion, and I think that each of these terms, again, will be quasi-modular. I'm not 100% sure about this. This was Beccaria and Cabo Bizet worked on this recently, and I think that that's their point, that they find quasi-modular forms appearing here. And for the one, so there is modularity, of course, everywhere. For the 1/16 VPS, which is the most interesting one because it captures black hole microstates, the index itself is not quasi-modular. It's related to some how was the name? Forgot the name of the function, but it's expected that it will have some kind of quantum modularity, not quasi or mock or anything, but quantum. But this I have no idea. So the BPS bound would be, so it's P phi equals, I think, h, maybe some with some prefactors. So all the intermediate ones for integer value of angular momentum, which it has to be quantized, they are BPS. Somehow we are saying that the extremal case is the only that contributes. Yeah. Right, right. Now I don't remember if it was on shell or off shell. Maybe, to be honest, maybe since we are in this half BPS subspace, things were okay. Now I forgot. Yeah, I'm not sure. Hmm. Right, right, right. Yeah, I'm not sure. I'm not sure. Thank you. Right. Yes. Yes. There's a. I mean, I think that probably it's very simple, but I have never done it, which is compute directly in the Lagrangian formalism. You should be able to get this just from the Lagrangian, but since we know the Hamiltonian answer.
Have you tried computing the expansion close to q.1 of the whole giant alpha?
Of this part?
Yeah, the whole sample.
I haven't tried.
It's not really physical, I assume that, I guess, but I was wondering in terms of resurgence properties. There are some Q series where a perfectly good Q series, but then you see that there's a bunch of poles, right, of any rational continuity.
Mhm.
And then when you expand close to, let's say, Q is e to the y, and when you send y to 0, you get some nice number theoretical / resurgent expansion. That seems nice enough. Yeah.
Yeah, so for the half BPS case, maybe things will not be very illustrative because, I mean, again, you have this nice identity. But for the other cases, this thing is very problematic. So maybe there's where you have to. Mhm. Okay, okay. Thank you.
Any more questions? So let's thank Martí again.
Thank you very much.